Hello, everyone. What we have today is a little bit of a supplemental thing. This is interesting stuff, but it's not necessarily crucial for what we're doing. Kind of just, you need to see some things, right? So we're talking about measurement and estimation and such. And so there's a thing we want to measure. And once we start measuring it, we're going to realize that there's a problem. Right? First off, I got this tape measure. I'm sure y'all have used one of these. And you'll notice at the end of it has a little bit of wobble in it. Right? And that wobble's there for a reason. So you can push it against a wall, or so you can hook it on the edge of a board. And I'm sure in your other classes they told you to maybe start at the number 1. I'm going to start at the number 3 because it's a little bit more convenient. I'm going to measure this thing, and it goes from 3 to 8 and maybe a half. I want to zoom in. I'll move us down a little bit. And you'll see that we can't quite get it all there, but that looks like about 5.5 inches. Well, it's kind of hard to tell. Are we really at 5.5? Is it a little bit short? We got a little bit of perspective issues. That's kind of weird. So we zoom out. If we were to write this down, this thing would be 3.5 inches. And we wouldn't put 3.50 or anything else because we know about sig figs. But there's a problem with sig figs. Sig figs are a set of rules that are supposed to tell you about the uncertainty in a measurement. But what if I have some alternate way of making my measurements? Right, what I have here is a set of calipers. The idea is that you just fit it over the object, and it tells you about how long a thing is. I'm sorry, I should have not said 3.5. I should have said 5.5. All right. So when we do this, does this actually help us any? Like most people would say, this is a more precise instrument. But when I look at it, it's about 5.5. And if I put some new batteries in this, if I add any, what I would get is a number that might be like 5.48 inches. I might gain 1 decimal point. But I still don't know exactly, right? The thing of it is, sig figs, if I use my 5.5 inch measure like this, well, there might be some warping in the tape. It might not conform, or I might have some error in measuring. But I can certainly say the error on this is toward a smaller measurement. It's no longer than 5.5. And sig figures lets me claim it's up to 5.54 because it doesn't care about how the uncertainty is constructed. So that's measurement. And that's not as much. The idea is if you have a better idea than sig figs for the type of measurement you have, you should actually state it. You actually state that this would be plus or minus 0.0, say 5 inches, or maybe plus 0.01 inch and minus 0.10 inch. You might say something like that. And that's giving the proper information with your measurement. Anyway, most of the time, we're going to do very simple, here's a thing, measure it, and you don't need that much precision, and sig figs are okay with it. But you will see that in other contexts. Now, your optional assignment was about doing some estimation. And the estimation is a way of saying, if I have a bunch of measurements and I don't know the uncertainty, can I get a ballpark answer? Right? I could ask how many of these ink pens would stretch just like that, one after another, from Pulaski to Whitfield, let's say. and we'll go by the interstate. So, get off exit 94 in Pulaski, you go to exit 73 in Wytheville. That's 21 miles. So, how many pins would it take to go 21 miles? Well, how many of these are in a mile? Depends on how long these are. And so we do some estimation, right? Maybe we don't necessarily know all the constants we're looking up, right? But we can get a ballpark for what's going on. So one of the issues is we have these weird rules in your textbook. I want to read them out to you for a minute. All right. An order of magnitude of a number is determined as follows. Express the number in scientific notation, which may be expressed, with the multiplier of the power of 10 between 1 and 10 as a unit. So let's say we're expressing this in distance, 21 miles. Well, that would be 2.1 times 10 to the 1. Number 2, if the multiplier is less than 3.162, which is the square root of 10, then you take the number of the power of 10 in scientific notation. So this implies that this would be 21 miles is approximately 10 miles. Let's double that. Let's do 42 miles. If the multiplier is greater than 3.162, in this case it's 4.2, this is approximately 100. You would do one larger in the multiplier. And that doesn't necessarily sound sensible, right? So imagine I'm driving from Pulaski to Wytheville. And sure, I can make the estimate that a one-way trip is 10 miles. It's off by a factor of 2, but that's, reasonable. But the round trip, a 42-mile trip, was also off by a factor of 2 the wrong way. We'd estimate it's 100 miles. Does it seem like you drive 100 miles round trip Wytheville to Pulaski? Or some equivalent distance? It seems a little off. So I want to talk about where that comes from. And the idea is that what are we doing when we take these numbers, and where did the square root of 10 come from? This seems like a very weird thing. So here's the thing. We already know when we're trying to do an order of magnitude estimate that what we really want is 1 times 10 to the x. We want something that looks like that. What this is counting zeros. All that is. So I want you to think for a moment. We're going to plot a graph. Here's our graph. And the y-axis is going to be number of zeros. And the y-axis is going to be an actual number. So there's our plot. You see previous work from before. There you go. You're seeing also the background because this is my house. Anyway, so we're going to put in, and we have to be careful here. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20. Yeah, you see where we run out. This will eventually be a logarithmic scale for a reason I'll explain. But the value of 1 should have exactly 0 zeros in it. Well, a value of 1 has exactly 1 0 in it. Right? Well, if we go out somewhere over here, where would 2 be? Well, that would be at 100, somewhere way off the screen. And this ends up being some sort of curve where if we think about numbers smaller than 1, right, 0.1, well, if we multiply it by 10, we would get to 0. So it really has minus 1 zeros. Right? What we're saying when we count zeros is we're actually counting decimal places. So 0.01 would be minus 2. And so this would curve off like that very quickly. And it would go out like that toward 100 being 2 zeros. That's a logarithm function. Right? Sorry, if we can check. So we're going to do the actual base 10 logarithm. I'm going to zoom in. Right? And we're going to do 1 base 10. Oops. 1 base 10 log is 0. 10 base 10 log is 1. 100 base 10 log is 2. 1,000 is 3. And we can check the other way. 0.1 is minus 1. 0.01 is minus 2. 0.001 is minus 3. This thing that we're describing, counting the zeros, is a logarithm function. But on our graph, what would the number 6, what would that be? Well, we can take the logarithm of it. It apparently has about 0.77 zeros, or 0.78 zeros. So that seems a little unusual, right? It's a fractional number of zeros. But we already got, when we talk about decimal places, negative numbers of zeros. So fractional is not that big of a jump, right? We can kind of live with it if we have to. And now we can get to where the square root of 10 went to. So what I want to do is look at 0.5, and instead of taking the logarithm, I'm going to take the inverse logarithm. And that's where that 3.162 number comes from. And if I happen to square that, I get 10. So what we get is that the square root of 10 is 10 to the 1/2. Let me zoom out so you can see what I wrote. 10 to the 1/2 is 3.162. So we can rearrange this. 0, what was the thing I was trying to say? 0.5, the inverse, right? So we have 1/2 log base 10 of 10 should be 0.5. And what we're saying is the square root of 10 represents the midway point between 1 0 and 2 zeros, or 0, if we go with 0.3162, it'd be between 0 zeros and 1 0. So it's a way of dividing the logarithmic scale in half. And the stuff on one side of it goes down and stuff on the other side goes up. All right, the idea is that when we're asking how many zeros a number has, we're doing this logarithm function. Let's see, what else is there? I do want to show you one more thing while I've got a few minutes. Why do we care about significant figures at all, right? I mean, if I look at this, right, I'm going to put in 0.5 and take the logarithm. Oh, clear. 0.5, take the inverse logarithm, and you get 1, 2, 3, 4, 5, 6, 7, 8 decimal places. And I'm sure if you had a TI something, one of these wonderful graphic calculators, you'd get 12 decimal places, or you'd get a symbol that represents the exact number in some way. Maybe it's a constant. But all of these things calculate based on some rounding. And to show you, what I'm going to do is take the number 9, and I'm going to do the sine, and then the cosine of that, and then the tangent of that. Now I'm going to undo that. So I'm going to take the inverse tangent, the inverse cosine, and the inverse sine. And we don't get 9, we get a little bit extra. Because at each step, it did a little bit of rounding. And then it went backwards and kept doing the rounding. And what it's really doing, it's not doing sine, cosine, and tangent in here. The idea is that when it has a function like sine of x, it really tries to calculate e to the log of sine of x. Because exponentials and logarithms are functions that these things are well programmed to do. Sines and cosines and tangents aren't. So when they try, and it may not be this, it might be log of e to the sine x or something like that. Or it might be some other algorithm. But the point is, if they can write if the calculator makers can write a function in terms of one that they know how to calculate well, that's what they do. And so this thing's doing thousands of calculations to get this number, and it's not precise to arbitrary precision. It's precise to maybe 12 digits, and it shows you 8 of them. But if you go through enough steps, you see the accumulated error that builds up. So when you make a measurement, there's a bunch of accumulated error, right? And so that's why I'm going to tell you that when we do problems, I do not want to see 8 significant figures because there's no way you can measure to that degree. And I'm going to pull my calipers back out here. I'm going to measure this, and it is almost 5 inches long. Very nice, handy calculator, almost as big as these pens. But can you tell me that that is 5.012357841 inches? No. You would say that's 5. You make a measurement, you report about the number that you can measure. You wouldn't give me all these numbers if you had to measure it because you can't calculate it. So what did we do before calculators? This is a slide rule. This one's special in the sense that it's circular, but it serves the purposes. And I'll show you a link to some regular straight ones. But this is simple enough. The idea is there's 2 scales on the outside. Notice there's a movable part here. All right. So the scales I'm looking at are labeled C and D. Those are doing this logarithm function that I have written down here, which I want to rotate my paper around so I can write something out. So, but the idea is if we have log of AB, well, that equals log A plus log B. All right. If you remember the other forms of this, log A over B is log A minus B. I believe that's right. I'm trying to remember this stuff off the top of my head, but the gist of it is this one has to be right because it's how these things work. All right, so we have this ruler, and I'm going to show you how it works. The idea is we're going to calculate something here. We're going to calculate 1.2 times, what's a good number? 3.7. And if I do it longhand, well, 2 and 7's 4, carry the 1. 1 7, 7, 1's 8. 12 7s are 84. And then 12 3s are 36. And then we'll have 4. 4, carry the 1, 4. 2 decimal places. 1 here, 1 there. And so 1, and that's about right. A number that's almost 4 times a number that's almost 1, but a little more, should give you a number that's a little more than 4. That's ballpark right. So we're going to do that calculation here. right? So there's our numbers. And what we're going to do is there's two flags here where the 1 is, and I'm going to put one of them at 1.2. Right? There it is. And you can see that there's a little bit of play here. I've got some space to wiggle. So there's already uncertainty in doing this. Then I want to rotate this around. I want to find 3.7 on the bottom scale. And you can see there's a little bit of error there. I'm trying to do this by camera. And so when we look at it, there's 4, 4, 1, 4, 2, 4, 3, 4, 4, and then 4, 4, 5 is the black mark, and the red is just a little bit on the side of it. So 4.44. Makes sense. But you could only get 2 digits out of this. There's no way you could get 8 out of it. Right? So if we had another number, so let me go to a different sheet of paper. Let's say we had 271 times 36. So if we do that, we have 6, 2 carry the 4, 2 and 6 is 12, and 4 is 16. Should check, by the way. And then we have 3, 7 threes are 21, 2 3, 6 and 2 is 8. So we'll have 6, 5, 7, and 9. We have no decimal places, so 9756. And very quickly, check with calculator. 271 times 36 is 9756. So I want to do that on this. Well, what I really need is to shift a bunch of numbers. I need 2.71 and 3.6. So that's what I want to do. I'm going to go back. I'm going to reset this up. And on one scale, I'm going to move it till I'm at 2.71. And it's about there. Then I'm going to go around on the bottom scale till I find 3.6. Out there. And what I'll get is 9.5, 9.6, 9.7, 9.5, maybe 9.775. Maybe that's what I got. And then I realized I took 3 decimal places off of this. I put them back, is 9775. And then I realized, well, I made some assumptions in this actual measurement. The best I can really do there is 2 sig figs. So this is really 9,800. But 2 sig figs on this calculation is really 9,800. The idea is that there was a time when calculation was actual measurement. And sig figs help you with that. Because this is the quality of the number you need, not the full story here. Right? So that's why sig figs got developed in a sense, is to account for your measurement abilities even when you're calculating. So, like I said, these things are nice. The usually C and D labeled are the things you do the calculations with, and what you notice is that they run around the circle from 1 to 10, or in a straight line from 1 to 10. And what they're doing, all right, notice that from 1 to 2 is about a third of the circle, but from 2 to 3 is less than a quarter, maybe a sixth. And from 3 to 4 is even smaller. And eventually the distances get much smaller. From 9 to 10 is a tiny wedge. It's a logarithm scaled out, right? If we had this on paper, 1 would be here, And then you do 2, 3, 4, 5, 6, 7, 8, 9, 10. Like that. They'd all bunch up near 10. But what this is doing is shifting everything around. Instead of multiplying two numbers, right, what we're doing is adding two distances. Here, we're taking the distance for 1.2, and we're going to add it to the distance for, what was my example, 3.7? We're going to add it to the distance for 3.7. And then so we get the distance that's the sum of that. That's how people used to do these measurements. And so that is your measurement and your estimation. The whole point of the estimation is you're just counting zeros. And the reason you're counting zeros is because of logarithms, and the logarithms and the ease in which you can do multiplication when you don't have calculators is why you have sig figs. And that's 25 minutes of my life I won't get back on that. So I'm going to save this video. That's supplemental stuff. You don't need to know this, but I think it's interesting. There's a whole lot of stuff like how the calculator works that's hidden from you. You just ask a question and get an answer from it. And there's a lot of details underneath that kind of stink. Like, oh, there's logarithms somewhere in things. And the logarithms are also following rules that you're learning in your math classes. So, yeah, that's about it. We have stuff. Anyway, that's enough.